In this video, we're going to take a look at the general power rule. So earlier in the course, we said that the derivative with respect to x of x to the n was equal to n times x to the n minus 1. And we said that that was true whenever n was a positive integer. So now we're just going to expand this statement a little bit and just make it a little bit more general. Instead of now working with just positive integers, we're going to now say that this is actually true whenever n is a rational number. Any rational number that is not equal to 0. So a rational number just means a number that can be written as a fraction. So for example, whole numbers like 2, negative integers like -3, and also fractions like, say, 1/2, maybe 7/4, -5/3 as well. So that gives you sort of an overview of rational numbers that we might run into. So let's try an example of now using this more general power rule to find some derivatives. I'll just do a few quick examples here. So let's find f prime of x. In part A, let's say that our function looks like the cube root of x. So part of the reason why we left the general rule until now is just that we may need a little bit of a recap here about exponents before we deal with some of these rational exponents here. So let's remember that f of x can be rewritten as x to the 1/3. So remember that if you're dealing with a root, whether it's a square root or a cube root, you can express that root as an exponent, and the denominator of your exponent here, in this case it's 3, is representing the type of root that you're dealing with. So f of x is the same thing as x to the 1/3. And now that we've got this rewritten, we should be able to use our power rule just as usual. So the power is going to come down in front, and the power on the x is going to decrease by 1. So that means f prime of x is going to look like 1/3 times x to the minus 2/3. And the way we get this power here is just thinking about calculating 1/3 minus 1. So 1/3 minus 3/3 gives us -2/3, and that's where this power comes from. Now it's a good idea to put our answer back in the original form that the question was in. So it was originally written out in terms of a root. So let's rewrite this. We'll have 1/3. And this negative exponent here is going to take the quantity down into the denominator. So we'll have x to the 2/3 down in the denominator. The denominator of the power here, that 3, corresponds to a cube root. So we've really got a cube root of x squared in our denominator. Again, the fact that the exponent is negative takes the quantity down into the denominator. The 2 corresponds to the 2 that stays on the x, so we keep an x squared here in our answer, and the 3 corresponds to the type of root that we've got in our answer. So there's a good answer to that problem. Okay, for part B, let's say our function looks like 7/x cubed. So again, we could rewrite this expression before taking our derivative. We'll want to think of this as 7 times x to the -3. The negative just coming from the fact that the x cubed was in the denominator of our function. So now that we've got this clearly written out like this, we can use our power rule. A mistake that students will often make, and that will slow people down, you might initially look at f of x here as a quotient, and you might think about using the quotient rule. Well, certainly it will work, but it's going to be a slow process compared to just rewriting this and then using our power rule. So now we can jump into it. F prime of x is equal to, well, according to our power rule, the -3 is going to come down in front. So we'll have -21 x to the -4. That -4 just coming from the fact that we're doing -3 minus 1 to get our new power. Okay, and if we want to give our answer in the form that it was originally written, we could re-express this as a quotient. Same thing as saying -21 over x to the 4th. You don't need the negative sign in the exponent anymore. Remember that negative up here just corresponded to the x to the 4th going down into the denominator. So there's our answer for the second part of the question. Okay, and let's do one more. Let's say f of x is 11 times the 4th root of x cubed. Again, let's write, oops, let's do some erasing here. Let's write f of x in terms of a rational power. So in other words, let's make the exponent clear here. We've got x to the power 3/4. The 3 coming from the cube that was originally on the x, the 4 just representing the type of root that we're dealing with here. So now according to our power rule, that exponent is just going to come down in front when we take our derivative. So 11 times 3/4 is going to give us 33/4. And our new exponent on our x is now going to be -1/4. -1/4, just coming from the fact that 3/4 minus 1 is -1/4. So we can think of it as 3/4 minus 4/4 will give us -1/4. Okay, and to give a nice final answer, we've got 33 divided by 4. And because of the negative exponent here, this quantity is going to get thrown down into the denominator. We'll lose the negative sign in the exponent as we do that. And remember that the 4 here in the denominator of the power tells us about the type of root that we're dealing with. So it's just a 4th root of x. So 33 divided by 4 times the 4th root of x. Now, one thing you might notice in part A and in part C, where we had roots coming up in our answer, notice that we did not rationalize our answer. Okay, so just to do a little bit of review here, remember that when you come up with a quantity like 1/√2, for example, often we rationalize this value, meaning getting the root out of the denominator. We would multiply the top and the bottom here by √2 to get √2/2. And that process there is called rationalizing. We do not need to do that when we have variables under the root. Okay, so in calculus, it will be common to see expressions like we see in our answer to part A, in our answer to part A here, in our answer to part 3. We've got variables under the root. There's no need to worry about rationalizing. So that's a question that students often have that I like to address when we're talking about the general power rule. So these two answers here, those are great. No need to do anything else to simplify those answers.